warranty on it and such.
All right, guys. I'm glad to see at least a few of you guys here. There were a lot more hands last time that went up. This is just for my purposes. I'm going to go ahead and pass around a sign-in sheet. I just am curious as to how many people showed up. Don't worry again. This is not going to affect your grade in any way. So for today's lecture, one of the things that we want to go through, make sure I'm This is material from chapter 6. It's the last few sections, and it's on a topic called mutual induction. Now, before we actually start talking about the equations for mutual induction, I really want to talk about what it means. So the definition of mutual induction it represents the ability of one inductor to induce a voltage across a neighboring coil. In other words, another inductor. And the mutual inductance symbol that we actually use to denote it is the symbol N. Now, remember at the very, very, very beginning of the semester, I do believe it was maybe like the second or third class, there were a certain set of assumptions that we had made for the circuit analysis that we were going to do. The first assumption that we had was that the wavelengths of the signals that were passing through our circuit were very long compared to the dimensions of the circuit, so that if there's any change in the circuit, all of the voltages and currents throughout the rest of the circuit are felt instantaneously, right? They don't take a certain amount of time to travel. The second assumption that we had made was that across any element whatsoever, the electric charge was balanced in equal but opposite pairs, so that the entire element happens to be neutral, right? So there are no sinks or sources of charge. The last assumption that we had made regarding the circuit analysis that we were doing in the class was that the elements in our circuit were magnetically isolated from one another, so that as there are time-changing currents in one portion of the circuit which are producing magnetic fields, those magnetic fields do not affect any other element in the circuit whatsoever. This is one of those instances in which that last assumption is going to be modified. In fact, it's going to be thrown away altogether, right? Now, the basic circuit that will kind of show to us what the concept is and how important it is the following. Suppose that we actually had over here a current source providing me with a current I1, and there is an inductor here that's hooked up to it. This has an inductance L1, and there's N1 coils or turns inside the physical inductor itself. Over here on this end of the circuit, we have a second inductor that has an inductance L2, and there is going to be what they call a mutual inductance between the two coils called M, and this inductor has N turns N2 as well. Now, one of the things that we talked about way back when we were actually deriving the IV characteristics for inductors was we talked about Faraday's law of induction, right? Remember that currents themselves generate magnetic fields, right? And as magnetic fields pass through coils, there's a surface area across those coils that the magnetic field happens to be passing through. Now, if you take the product of the magnetic field strength times the cross-sectional area, you get what they call a magnetic flux. And And if you happen to have a time-changing magnetic flux, what that does is it induces a voltage across the coils. That's how we derive the IV characteristics for an inductor, right? So over here, for example, we have this current that's being fed through this inductor, and suppose that there is a magnetic field absolutely everywhere in space that's being generated by this current. And suppose that the magnetic field, just some representative lines, suppose that the magnetic field looks something like this. I'll draw one more representative magnetic field. And so all of the magnetic fields on the outside of this are going up like that. And notice that on the inside, they're going up like that, right? Now, this is a magnetic field that we can call V1. The fact that this actually has a certain cross section, right? Notice that there is a magnetic flux that's actually penetrating through these coils. And what this is going to do is, according to Faraday's law of induction, is it's going to generate across this inductor, it's going to generate a voltage that I call V1, right? Now, this magnetic field is not only going through the coils here, but that magnetic field exists everywhere in space. Not only on the inside of this, but notice that it's actually extending beyond the inductor, the physical location, and it's extending outwards. So this magnetic field, if you keep on drawing these magnetic field lines, notice that eventually they're going to cross through the coil that we have over here that is electrically isolated from the first portion of the circuit. So over here, we actually have the same magnetic field that's being generated by this current, except now it is in a new location and it is penetrating through the surface area of this coil, right? Due to the fact that now we have a magnetic flux over here, according to Faraday's law of induction, what's going to appear across this inductor? There's a voltage that's going to appear, right? So over here, there is going to be a voltage V2 across this coil, which is electrically isolated from the first set. And it's due to the fact that this current I1 is generating this magnetic field through those coils as well. Now, in terms of over here, this voltage, due to the fact that it is this voltage V1 that's associated with L1, that voltage has a special name. That's what they call a self-induced voltage. So the self-induced voltage here is going to be what we call V1, and it is L1 times the time rate of change of the current that happens to be flowing through that inductor. Now, I'm going to place a red circle around here for a very good reason, which will be explained here in a second. Now, there's also going to be a mutually induced voltage across these coils, and this is what they call the mutually induced voltage. And this voltage V2 is going to be the mutual inductance between the two, and the current that is generating the magnetic field, which is changing the flux, is I1. So it is also a product of the time rate of change of the current I1, not that's flowing through this inductor, but it is flowing through the original inductor. I'm also going to place a red circle there for reasons that I'm going to explain in a second. Now, very conspicuously, one of the things that I left off from this voltage V1 and this voltage V2, whenever you specify a voltage, you need to specify a magnitude, but what else do you need to specify? You need to specify a polarity, right? So over here, we need to know whether this is plus and this is minus, or this is plus and that is minus, and similarly over here, this is plus, this is minus, or this is plus and that is minus. So we need to specify both the magnitude as well as the voltage polarity. And the way we're actually going to do that is we're going to appeal to two things. So to establish the polarities, for both the self-induced term as well as the mutually induced term. So for the self-induced voltage, well, we use the passive sign convention. Right? So here we're going to use the passive sign convention. Which means immediately over here, when I take a look at the voltage polarity across this inductor, what direction is my current flowing in through that inductor? From top to bottom, which means that this voltage polarity has to have plus up top, minus on bottom. So for the self-induced term, we will always use the passive sign convention to establish this polarity. For the mutually induced voltage, we're going to establish the polarity by using what they call the dot convention. So here polarity is established by what they call the dot convention. It will turn out that this polarity and this dot convention depends very intimately on how the coils are wound, whether both this coil and that coil are clockwise, or whether one is clockwise and the other one is counterclockwise. So here, the polarity will be established physically by how the coils are wound. In other words, they depend on the physical construction of each one of the coils. So, i.e., the physical construction of the coils. Now, the dot rule itself, or the dot convention, can be found in multiple places in the textbook. I'm going to go ahead and repeat it for you guys here. So this I'm going to get rid of. And the dot rule, or convention, which can be found on page 190 of the text, tells us, and it's a bit wordy, so bear with me, it tells us that when the reference direction for a current enters the dotted terminal of a coil, the reference polarity of the voltage that it induces in the other coil is positive at its dotted terminal. Now, this deserves quite a bit of an explanation. I don't know about you guys, but if I read this, when I read this for the first time, it was extremely confusing to me. It really doesn't make that much sense. So let me go ahead and actually interpret what this actually means for you guys physically. So the way we're going to approach this is I'm going to consider two coils. Based on the physical construction of the coils, that's going to determine for me where I place the dots right? And we're going to be taking a look at the magnetic fields to see how it's going to induce a particular voltage, right? After we establish the dots for these, we're going to take a step back and take a look at what consequences these have once the dots are actually in place for actual circuit analysis in terms of the circuits that we've been considering, right? So let's talk about the following example. So this is example to establish dots. So how to establish dots at coils. And this is problem 6.43D in the text. Now, in the text, they have the following system. And I'm going to see if I can draw it relatively large. We have two holes here. And on the outside of this, we have one large rectangle, right? So this itself is made out of a ferromagnetic material. Now, in this, we actually have, on the top part, we have a wire physically that starts winding around like this. So I'm going to call this terminal 1 and this over here terminal 2. So if you can imagine this shell-type transformer, on the back end, we start with a wire and then we wind it around the front. We wind it around the front again like so, and then the wire comes back out. So notice that we're actually winding it in a particular direction. There's a second coil or a second inductor where we have our third terminal, and this goes around the back, comes back around the front, goes back around the back again, and then comes out the front like so. So notice that here we start with our wire and then we wrap it around like so again, right? So here we actually have the physical windings of the coils. This particular structure is relatively common. It's what they call a shell-type transformer. Now, here one of the things that we want to do is we want to be able to establish for both of these what their actual dots are in relation to this dot rule, right? And the way we end up doing it is going to be the following. And we're really going to have to use the right-hand rule, if you guys remember, for magnetic fields. For magnetic fields, where they happen to be generated, in terms of their direction, you place your thumb in the direction of the current, and you curl your hand till you get to what they call the field point. Perpendicular to your palm will be the direction of the magnetic field. So suppose over here in the first coil, suppose that I place a dot on terminal number 1, and what I do is I feed in, entering into the dot, a current that I'm going to call I1, right? Now, I1 itself, this current, is going to generate a magnetic field everywhere in space. And in particular, it's going to generate a magnetic field on the inside of the coil, right? So if you can actually picture in your mind's eye, imagine that this was the ferromagnetic material. The current is actually being fed in through the back. So you're placing your thumb in the direction of the current. And I'm interested in the magnetic field that's penetrating through that right there. So notice it is on the inside of this. So notice that my magnetic field through the coils is pointing downward. Right, so over here, the magnetic field that is actually being generated by this current I1, it penetrates downward through there on the inside, and it's also going to penetrate down this way through the second set of coils. Yes?
The right-hand rule for coils like this was to
You can do that too. So notice that over here, for example, I'm interested again on the magnetic field on the inside. If my current is pointing this way and I grab it, on the inside of the coil, notice that my palm is still pointing down. So there are multiple right-hand rules. Right? Now, this over here, again, is generating a magnetic field down here, going down this way, and it's going to generate the magnetic field coming down this way through the second coil as well. Now, over here, depending on where I feed in an entering current over there, it can either add to the magnetic field if the magnetic field produced by the second current is in the same direction, or it can subtract from it in the sense that it would go in the opposite direction. The one where it happens to add, as I feed in the current entering, that's where my second dot is going to go, because superposition is going to increase the flux, which is going to increase the voltage, right? So here we have literally two possibilities. Suppose that I actually fed in a current going into terminal 3, right? Now, according to my right-hand rule, if it's going in and I'm interested on the inside of this, notice that I would have to turn all the way around, right? And that magnetic field generated by this current entering into terminal 3, it would go upwards. Notice that that is subtracting away from the magnetic field that was there already. Now, if I actually feed in the current into terminal 4, right? So here, my current's going in this way. On the inside of this, notice that here, my magnetic field is now going in the same direction as the magnetic field that was already there. So if I actually had this current, let's say I2 going into there, on the inside of this, this magnetic field produced by this current would be going in the same direction there and the same direction there, which means that this terminal and that terminal happen to be dotted. Right? So it really has to do with superposition, finding the magnetic fields depending on where you feed in the current and making sure that they add up to something bigger so that you get a larger magnetic flux. Right? Now, this is how you establish the dots inside the physical windings, but let's take a look at what this actually means and how to interpret this when we're actually dealing with practical circuits. Right? For a practical circuit, there's a simpler way to remember this. So this is on the interpretation or understanding the dot rule. And it is that if both currents enter or leave their dotted terminals, then the mutual term is positive. Conversely, if one current enters its dotted terminal, and the other current leaves its dotted terminal, then the mutual term is negative. Now, let's take some examples to make this very, very specific. In the first example, I have the following coil. It has a self-inductance L1. Over here, we have another coil of self-inductance L2, and there is a mutual inductance M between the two of them. Over here, we're going to have exactly the same system. So self-inductance L1, self-inductance L2. There's a mutual inductance term between the two. I'm going to feed in a current I1 into there, a current I2 into there, current I1 into there, current I2 into there. And lastly, over here, I have my dots. So the dots represent how these coils are literally physically wound. Over here, both of the dots are actually on the top. While in this example, we actually have a dot on the top and we have a dot on the bottom. And we're interested in the voltages V1 and V2 across each one of the coils. So let's take a look at the voltage V1 over here, as well as V2. We're also going to have a voltage V1 over here, a voltage V2 over there. Now, the voltages are across each one of these, like so. And let's concentrate on this voltage V1 across this inductor first. Right? Now, the fact that there's a current I1 flowing through this inductor, right, means that there's going to be a self-induced voltage, right? And notice that the current over here that's entering here is going in the direction of the voltage drop, right? Which means that when I have my self-induced voltage, it is L1 di1 dt. And what is the sign on the self-induced voltage? So notice that this current, is it going in the direction of the voltage drop or voltage rise? Voltage drop, which means according to the passive sign convention, this has to be positive, right? Because it's going in the direction of the voltage drop. So this is positive. There is also going to be a mutual term, right? Which is equal to the mutual inductance between the two coils, right? And it is this current over here that's creating a magnetic field. That magnetic field is penetrating through these coils. And so here, this is the I2 dt, right? And again, it's because this current is generating a magnetic field here. It's generating a time-changing magnetic flux. Right? Question is, well, what is this? Right? What is the sign here? Now, if you actually take a look, you have to take a look at both coils. According to this, if both currents enter or leave their dotted terminals, the mutual term is positive. If one current enters its dotted terminal and the other leaves its dotted terminal, the mutual term is negative. So over here, if I take a look at I1, I1 goes in through here, it hits its dotted terminal, then it goes through the inductor. So this one is entering its dotted terminal. Over here, I have my current I2, it hits its dotted terminal, then it goes through the inductor. Both of those are entering their dotted terminals, which means, according to what I just said, this mutual term is positive. Let's take a look at the voltage V2 over here, right? Now, I have a current I2 flowing through this inductor, which means there's a voltage here, L2 times di2 dt. Who can tell me what the voltage polarity on this term is? It's positive, right? Notice that the voltage here has been defined in such a way that the current is going in the voltage drop, in the direction of the voltage drop. So here, this is positive. There is a mutual term, which is a mutual inductance times di1 dt, because this current over here is producing a magnetic field there. Right? Question is, well, what's the sign on this mutual term? Over here, this current is entering its dotted terminal because it hits the dotted terminal before going through the inductor. Is this current entering or leaving its dotted terminal? It's entering. Both of them are entering. Therefore, the mutual term here is positive. Right? Let's take a look at the example over here, the second one, where we actually switch how the coils are wound based on the dots. So for V1, there's a self-induced voltage, right? And it's going to be L1 times di1 dt. And who can tell me what the voltage polarity on that is? It's positive, right? Again, this current is going in the direction of the voltage drop. So that's positive. There's going to be a mutual term over here, and it's the mutual inductance times di2 dt, because this current is generating a magnetic field there, it's generating a magnetic flux. Right? Now, this current, is it entering or leaving its dotted terminal? It is entering. How about this current? Is it entering or leaving its dotted terminal? It is leaving. It goes through the inductor, then goes out through the dot, which means it is leaving. This one's entering, this one's leaving, which tells me that this mutual term is negative. For V2, the voltage across this coil, who can tell me the first term? It's going to be positive L2 di, which I? di2 dt. So this is the self-induced voltage, and it is positive. There's going to be a mutual term over here, and it's the mutual inductance between the two. And what am I multiplying that by? di1 dt, because it is this one that's generating the magnetic field and magnetic flux. Now, this one is entering its dotted terminal. This one is leaving its dotted terminal, which means, who can tell me what the sign on that is? It is minus. Yes?
So the dot kind of indicates north and south for the magnetic field?
It's not that it indicates north and south. It tells you how the coils are constructed, how they're wound in relation to one another. Right? Exactly. So one of the things that is going to happen with these circuits is they're never going to tell you, like, oh, this inductor over here in the circuit is wound when you're looking from the top down in the clockwise direction, right? They're not going to tell you, if you're looking at this other coil, if you're looking down, it's going to be wound in the counterclockwise direction. It's too much information to actually be giving. So they summarize how these coils are actually wound, how they're physically constructed, by telling you where the dots are. And the dots are set in such a way that you can determine what the sign on the mutual term will be if you actually have these currents entering and leaving. Let's go through another example, right? Because this still is probably a little bit abstract. Let's go through something a little bit more sophisticated. So I'm going to leave this one up. But let's take a look at another example that's in the text. And this is example 6.6 in the text. Now, this circuit contains a current source IG. It is hooked up to a resistor there. We then see our first inductor. There's another resistor there, another resistor there. The bottom portion is now complete. There's one more element. It is up here, and it's an inductor. This is a 5 ohm resistor, a 20 ohm resistor, a 60 ohm resistor. This has a self-inductance of 16 henries. This has a self-inductance of 4 henries. There's also a mutual inductance between these two coils of 8 henries. And their dots, first one is there, second one is there. Right? So notice that they're telling us how these coils are wound with respect to one They also defined for us already, they defined for us some mesh currents here. So we have IG defined to flow along that mesh. There's I1 to flow along the perimeter of this mesh. And lastly, there's a mesh current, I2, that flows along the perimeter of that mesh. Now, what they want us to do is to write the mesh current equations for mesh 1 and mesh 2. Right, so here, we're going to use KCL, or KVL, I'm sorry, to write down mesh current equations. So notice that this circuit is a lot more sophisticated than the one that we had over there. I should be able to do it. So let's concentrate on this mesh first. So I'm going to use KVL around mesh number 1. So the sum of the currents or voltages around this mesh have to add up to 0. Now let's avoid the inductor, at least for the moment, right? Let's take a look at the resistor. So suppose that I move in the same direction as I added my voltages as the current I1. The first element that I go through is my 20 ohm resistor. What mesh currents exist in that 20 ohm resistor? I1 and I2. Notice that I'm going in the same direction as I1, but I'm going in the opposite direction as I2, which means that the voltage that I pick up is 20 I1 minus I2 when I go through my resistor. I then go through my 5 ohm resistor, and I'm going in the same direction as I1, but I'm going in the opposite direction as IG. So the voltage across the 5 ohm resistor is 5 I1 minus IG. Right? Then I go through my inductor, right? So here my current I1 is going this way. I'm adding my voltages in my loop like that. When I go through this inductor, am I going in the same direction or opposite direction as I1? As I add up my voltages. Same direction. So the self-induced term is plus 4 henries times the current flowing through that inductor, which is di1 dt. So this is the self-induced term. Then we're actually going to have a mutual term, mutually induced voltage. Right? And the mutually induced voltage, well, it's the mutual inductance times the time derivative of the current that's flowing through the other coil, right? So there is a current that's flowing through this coil that is setting up a magnetic field over there, right? Now, here we actually have to make a choice, right? Flowing through the 16 Henry inductor, we can either say it is IG minus I2 or I2 minus IG, right? So let's pick the first one. Let's say my net current is flowing down this way, right? That would be IG minus I2. So this is the mutually induced term, or the mutual term. And now to figure out the polarity on this, I have to take a look at both currents to see whether they're both entering, they're both exiting, or if one is entering and one is exiting. So I1 over here, is it entering or exiting its dotted terminal? It is entering its dotted terminal. IG minus I2 over here, we've chosen its direction to be downward. So if it's IG minus I2, is it entering or exiting its dotted terminal? It is entering. I1 is entering, IG minus I2 is entering, therefore the mutually induced term is positive. Yes? We're going to do it the other way too, right? So this is one of the results. Notice that all of this over here, if I actually chose the reference direction for this current, it's not going to be changed at all, right? So if I chose the second one, So here I have, I'm going to copy all of this down once again. Now I still, when I go through this, I still have a self-induced voltage, and it's 4 henries times di 1 dt. But now for the mutually induced term, I'm going to have the mutual inductance times the time derivative. Now I'm going to say that the net current is not going down this way, it's going up that way through this inductor. That means that the net current is a superposition of I2 and Ig, and it is I2 minus Ig. That has to equal 0. Now, over here, I1, is it entering or exiting its dotted terminal? It's entering. Now, over here, I said it's I2 minus Ig. Is that current entering or entering its dotted terminal? Yes. I said entering or entering, didn't I? Yeah, so it's going through the inductor, and then it's touching its dotted terminal, which means I2 minus Ig is exiting. This one's entering. This one's exiting. This mutual term is negative. Now, notice that one of the things that you can do is a negative sign I can actually push beyond a derivative. So I can use that negative sign over here, turn it into a positive sign. This is going to flip, and you get the original one that you had before. So this is for KCL around mesh 1. Notice that we can do the same thing for KCL around mesh 2. All right, so let's do that. Let's get rid of these. So now I'm going to use KVL around mesh number 2. So the sum of my voltages around this mesh have to add up to 0. So now I'm taking a look at this one. Let's leave the inductor till the very end again, right? I'm going to go through my 20 ohm resistor, and I'm going in the same direction as I2, but I'm opposing I1. So the first term that I pick up is 20 I2 minus I1. And I'll copy this down here too. I then go through my 60 ohm resistor, only I2 exists there. I'm going the same direction, so it's plus 60 times I2. And then I go through this inductor, right? Now I'm adding up my voltages in my loop in this direction, right? Which means that I want to respect my passive sign convention. I have to pick I2 to go first, right? Because of the fact that it's going in the same direction as the voltages that I'm adding up in my loop. So over here, the self-induced term, if I want it to be positive, it's going to be the 16 henries times the time derivative of I2 minus Ig, like so. Now for the mutually induced term, actually I think, yeah, so let's do the following. The mutually induced term, it's going to be the mutual inductance, right, times the time derivative of the current flowing through here, because this current I1 is generating a magnetic field there. So here, for both of them, it is the I1 dt. The question is, what's the sign on these? Now over here, I1, it is entering its dotted terminal. I2 minus Ig, I2 is the dominant current. It goes through the inductor, and then it goes out through its dotted coil, or its dot. So this one's entering, this one's exiting, which means that has to be negative. Now, I was hoping, and it turns out that I didn't do this, I don't want to say as carefully as possible. One of the things that you could have done, no, let's not do that. So I thought there were going to be two equations from this. right? But it turns out that there's only one. I didn't think it all the way through. At least we got the right result. This is all I have for you guys today for the supplementary lecture. There will be another lecture on Monday as well as on Friday, and we will be going through second order circuits, in particular the series and the parallel RLC circuits, both the natural and the step response. And I'll see you guys next time. And thanks for coming.